Thank you for that introduction. Now I hope I can live up to it. Um, all right, well, thanks again for joining us today. So in the last lecture, we talked a lot about human factors in the more traditional sense. So thinking about how to design systems with keeping humans in mind, how to design experiments, and how we can sort of take some of these abstract topics like trust and try and come up with concrete ways to measure them and try and incorporate that back into our design process. So today we're going to be talking about a different facet of humans in intelligent vehicles, thinking a little bit more about how we can predict, model, or estimate driver behavior. So in the last lecture, we talked a lot about driver assistance systems, since that's a lot, but that's the sort of more prominent place where some of the human factors topics that we talked about before really come into play. But today we'll be talking a little bit more about these higher levels of autonomy, where we really need to capture some of these behaviors and predictions of how drivers will drive. And one of the key things that I think we would like to take away from this is what are the different things that go into modeling different aspects of behavior. So today we're going to basically be spending most of our time talking about a taxonomy that basically categorizes or tries to classify different aspects of driver behavior, and try to basically give some insight to how people typically address them. So we won't be going through sort of specific papers, but really thinking about classes or ways we can approach the problem. Because I think one of the biggest challenges in driver behaviors is that there isn't one method that is like the method you need to know or the method you need to use. A lot of it depends on the problem you're considering and what your downstream tasks are. So we're going to basically be doing a very wide overview of the different approaches that are common and go through those different things. And we'll have a few examples throughout, but most of the reference are actually a part of a survey paper that we were recently working on. So a lot of the content that we'll be talking today has been provided by Kyle Brown, who's a graduate student at Stanford, who has really sort of done a lot of good work surveying a lot of recent developments in driver behavior modeling. And we also have some additional context for modeling human behavior from my graduate student, Joe. All right, so hopefully we can have some interesting discussions too. So at any point, if you have any questions, feel free to either raise your hand, drop a note in chat, or speak up, and we're happy to chat about the different aspects of behavior. All right, so just a friendly reminder. So one of the things we really want to be trying to think about is how we can, again, design these systems so we can have these autonomous vehicles or intelligent vehicles that, again, are operating out with people in the real world. So often we don't want to just take sort of the technical tools and these lower level things, but we really want to think about how we can incorporate the human. We want to think about ways we can really incorporate good experiments, again, to make sure that we are rigorously testing our interactions and making sure that we're safe, but also really thinking about when these systems are deployed, what are the sort of system or what are the sort of scenarios that they will encounter, and what might we need to consider in these systems in deployment. So as just a quick motivation for why we kind of need to think about behavior modeling, so I'm going to show two quick videos. So this first video is, I will admit it is an old video, but this is a video of a Google car driving. So it approaches this intersection, and it's trying to figure out whether or not it should go through. So as you can see, it's having a bit of a hard time. Now, to give a little bit of context here or comparison, so here's how humans handle much more complicated intersections. So when humans drive, we're really good at understanding context, understanding what other agents around us are doing, what they will do in the future. And we're constantly making these predictions and estimations about what's going on in the environments around us. So even though, like I said, this video over here is a little dated, it's still, these sorts of really interactive scenarios are still very challenging for autonomy. So one of the things we want to try and think about is how we can take different models of human behavior to give our autonomous agents or our intelligent vehicles the same sort of insights that people have, or we can also think about how we can try and mimic and recreate these human behaviors. So by carefully modeling and understanding how people operate and how they behave in these sorts of crazy situations, we can hopefully design better autonomous systems. All right, so that was sort of our quick introduction here. So today, again, we're going to be talking about, we'll first introduce a framework so we can basically think about how we can talk about the different aspects of driver behavior modeling or driver behaviors and cast it into a formal framework. So we can basically sort of more concretely identify where different models or aspects will come into play. And once we sort of have this unified framework that we can discuss and talk about, we'll talk about these different tasks that are commonly addressed in driver modeling and talk about some of the ways they are both represented and then solved. And depending on time, we might touch on some pedestrian prediction. Although I will say that pretty much all of the things we talk about in the modeling for driver behaviors are quite general. So they can work for both pedestrian prediction, but as well as some of these pretty much any sort of human behavior or system behavior modeling and prediction. All right, so unless there are any questions, which again, I encourage you to drop some notes in chat if you do have questions along the way. We'll jump into talking about some of these formulations. Okay, so the way we're going to start sort of formalizing or sort of the framework we're going to use for driver behavior is going to be as a partially observable stochastic game. So this is just a very general framework that's meant to capture how different agents interact and basically come up with different variables to represent different aspects of the agents. So at the very top, we have first our kinematic state of some agent I. So the notation that we'll be using is subscript I is going to denote the agent. And note that everything here is going to be time varying, which is denoted by this superscript here. So X is going to be our kinematic state. So when you're thinking about something like a driver behavior, this can be basically the kinematics or dynamic state that represents the motion or physical state of the agent. So you can think of this as position, velocity, acceleration, things like that here. Okay. Then we also have an internal state. So this is something that might not be directly observable, but this is going to be some sort of latent state that's going to influence things down the road. So in the case of driving, we can think of how this might be something like the underlying goals of the agent. So what is the task that it's trying to achieve? Is it trying to maintain its lane or maybe execute some lane change? But we'll talk about how this can also represent some other sort of internal parameters, like whether or not the driver is attentive or distracted. Maybe they are an aggressive driver or a very passive driver. So this is basically some internal set of parameters that basically will guide and influence the next part, which is basically the control of the agent. So U is going to represent our control actions. So again, these are basically the inputs to the vehicle itself, or basically what these inputs or actions are going to be. Depending on what model or what sort of level of modeling you're considering, this can either be very low level actions. So for a car, this can be directly the throttle or the braking pressure that's being applied, or this can be a higher level action, saying something like what is going to be the set speed that you're trying to follow. So this is a very abstract representation that can basically mean many different things. Okay, so next we have our observations. So in most scenarios, we don't have direct access to many of these variables that we've mentioned thus far. So we might not be able to observe the state or the internal state in particular directly, but we can get observations from our sensors that we can then use to make inferences about these different variables here. So that's part of what makes this this framework partially observable, since we assume we don't have direct access to some of these other pieces or components. So to connect all of these different variables together, we have a state transition function. So these are going to be some sort of dynamics or some sort of model that takes in your states and inputs and basically propagates this forward. And we'll talk about we'll have a graphical representation of this shortly to make it a little bit more concrete about how all these connect. But this is basically going to be what moves us from our current state to our next state and forward. We also have our observation function. So this is basically going to be the sort of abstract function that's going to eat in all the true states and spit out what we're observing. Similarly, we have some internal state transition function. So this is basically going to be what's evolving our internal state over time. And this is something that's probably the most abstract and difficult to understand here. But again, hopefully, once we get to the graph, it'll be a little bit more clear how these things evolve. And finally, we do have our policy. So this is going to be the function that is guiding what our control is. So here we say it's a function of our internal state. You can also add that this is perhaps a function of our current state. But to keep it a little bit more concise, we assume this is sort of contained here. But what this kind of shows and highlights is that the way you control your vehicle is basically going to be dependent or a function of this internal state. So again, if we are thinking about aggressive driving, this is going to be basically the variable that kind of guides and influences our policy here. Okay, so this is sort of the formal notation that we're going to use. But as I mentioned, let's move to a graph so we can kind of understand sort of how all these things fit together. Okay, so as I mentioned before, we have our states. So this is going to be the physical states of our system at time t. We also have a internal state, B, here. And this is what's going to define our inputs, or basically how we're controlling and how we're going to move our vehicle, for example. All of these come together to determine what our next state is going to be. So again, we're basically going to think about this as evolving over time. So this is basically where this state transition function comes into play. And here we've noted that this is all for a single agent. So this is subscript 1 to basically show that this is for a single agent. But as we're thinking about traffic and driving, usually we don't want to consider just a single agent in isolation, but we want to think about how we can stack this and sort of represent this for all of the agents in our system. Okay. And for all of these different states, we will then receive observations. So again, this is basically going to be something like sensor readings or maybe even some inference that we're doing. And all of this will come in to basically take us to our next step for the belief here. Okay, and as always, this is for all different agents. So we're thinking about basically all agents in our scene or agents that we're sort of considering at this time. Okay, let me build this up. And again, we don't want to just think about sort of this current state and our next state. Really, we have this sort of going in both directions. So we'll have a history of time that we're considering and then mapping this into the future. So we can basically extend this out in both ways. So we can have basically previous observations from time 0 or perhaps in some window to the current time, and then we can propagate this forward to think about what this future time is going to be. Okay. So one thing that's good to note is we do have different observations for these individual agents that come in at every time here, but we also can basically collect all of these observations into what we'll denote as ZR. So this is the observations for the robot. So if we're thinking about an autonomous vehicle that is trying to predict other agents around us, we'll basically represent all of these observations that we have with this subscript ZR here. So the difference here would be this is basically what our ego agent or what the agent we're sort of thinking of from their perspective will be represented, whereas each agent also sort of has their own observations that they're making about the world. So it's important to note that these might not be exactly the same, depending on what sorts of information you have access to. Okay, so this is basically this graphical representation. And we'll basically use this to start thinking about how we can map different driver tasks to these different, sort of different variables and different pieces in this graph here. But does anyone have any questions about this sort of high-level formulation before we move on? All right. Well, if you do have any questions, again, feel free to drop a note in chat or raise your hand and we'll try and get your questions answered. All right, so as I mentioned, now that we sort of have this framework and this model that we want to sort of build off of, we're going to start thinking about what are this canonical driver modeling tasks, and how can we go about sort of formalizing them and thinking about the important pieces that we want to consider for each of these different tasks. Okay, so one of the probably most general tasks that we might think of is state estimation. So basically, when we think of state estimation, what we want to do is we want to basically take all the observations that we've received up till some time and start making some inferences about our current state here. Okay, and I call this a driver modeling task, but as I mentioned, this is a more general task where we're really just trying to figure out what sort of the state of the world is so we can make better decisions based on that here. The next one would be intent estimation. So again, we are primarily building on our observations that we have of our world. So building on these, this Z, and we're trying to make inferences about this internal state to be. So when we think about intentions, again, these are going to basically be goals or things that are sort of guiding how we're going to maneuver our agent. So does anyone have any ideas of what some examples of intents might be in driving? Does anyone want to drop some things in chat? What are some modes of intent that we might have in driving? That's a very negative intent you have there. But yes, so often maneuvers are associated with these different intents. So this is great. So lane changing is one. Turning right is a great example, one that might be to follow some sort of route. Exactly. I like the accelerate and decelerate. One of, I think, the important things to remember is that the level of abstraction is sort of up to you. And this is sort of when you're designing your model and thinking about what you need to do with your model, this can kind of influence that. So yeah, so when we think about these high level actions or these basically goals that we want to attribute, this is what these intents are going to be. Good. Ooh, I like avoid tolls. That's a good one because that will significantly change your very high level behavior. So this is great. All right. So the next task we'll be thinking about is trait estimation. So now this is something that in the diagram, it actually looks very similar. But this is trying to capture different traits or aspects of the driver. So, and again, feel free to drop some ideas of what some driver traits might be. But actually, I think, and to link it back to some of these other examples, some traits might also have some overlap with intentions. For example, the avoid tolls one, maybe one of my traits is that I'm a stingy driver. So I don't mind taking longer routes to avoid tolls. And this sort of parameterization or this representation of my trait might have some overlap or influence my intentions. Does anyone have any other ideas of what some interesting traits you might want to estimate for a driver might be? Aggressiveness. Yeah, so that's one of the sort of canonical examples that we often think about is how aggressive or how risky things are. Good. Reaction times is a great one. And actually, often people try to connect things like aggressiveness or how passive you are, maybe to take the other one in, try to take this into or characterize this by reaction times. Distraction or texting while driving is another great one. So trying to model the level of attention. And that's something that can also be done just internally, but trying to model these for other agents is also very, very hard. And age of the driver is great. So you can often sort of try to categorize or classify different aspects of the driver in this sort of this piece here. And I think often as relatively, I'm sort of assuming relatively young people, we often try to think of older drivers and what are some of the characteristics they exhibit, but actually teen drivers exhibit very different drivers or driver behaviors than more experienced drivers. So often you're very concerned about sort of the tail ends there. Okay, great. So again, feel free to keep dropping things in chat. I think it's good to sort of collect as much insight as possible. But we'll keep moving on. So probably one of the most important aspects of driver modeling is the motion prediction. So this is basically taking your observations up to the current time and trying to predict how the agent is going to move or behave moving forward. So this prediction part becomes very important when we start thinking about trying to take these driver models and incorporate them into some motion planning, or incorporate this into our autonomous vehicle itself. So this is the probably one of the main problems that we'll think about. There are many other related tasks that you can cast as a driver modeling problem. For example, estimating risk or sort of likelihood of things like collision, anomaly detection. So when people are performing perhaps unintentional actions versus something with strong intent. We can also think about coming up with models that have a very specific purpose in mind, like simulation, or as we mentioned before, perhaps trying to come up with models that we can then use for imitating or coming up with more human-like motion. But today, so basically what we're going to do is we're going to focus on these three tasks here. So we can start thinking about how we can model and represent these different pieces, and hopefully then think about how we might pass this into our autonomous vehicle down the road. Another thing I really want to encourage people to do is while we're thinking about these different tasks is to, again, try and think about how we can relate this to some of the things we talked about in the last lecture. So how do all of these different pieces perhaps influence, or how might they reflect on how much we trust the agents, or how would this affect something like how we validate or test our system? All right, so again, if there are any questions, feel free to chime in, but we'll keep moving on. So the first, we're going to start talking about intent. So as a quick aside, let's talk a little bit about what intent is. So I think, let's see. So first we have a question from Betty here. So actually, so this is a great question. So if you have, so the question is, can you apply the same methodology if one knows another vehicle is autonomous? So this is a great question. And I think the answer is, depends on how much you know about the other agents around you. So if you know they are also autonomous, then it might be much easier to do something like motion prediction, because hopefully the agent itself is predicting what it's going to do or has some forward prediction. So you might be able to leverage that insight from the model as provided of the agent here. You can also, if everything is autonomous, the need for motion prediction or estimating a lot of these things kind of go away, because there's usually an assumption that you would be able to share more information. But the formulation of these methods themselves are very general. So you would be able to apply this to any other agent, be they human or autonomous. Great. And so for, to answer some of these other questions, oh, I love that there are so many questions. Okay, so skill level estimation. So this is a great question. So this actually ties back to some of what we're talking about with perhaps age relation. So you can, so when you often model things like teen drivers, you often model this or represent this as experience, and you try and model the difference that occurs, or the different characteristics drivers experience or exhibit based on experience. So there's actually a lot of work in trying to model these different levels of experience that way. So this would basically come into play, again, if we're trying to be very, tie everything back to these tasks, this would tie into this trait estimation piece. So for the intent estimation, so we'll talk in a moment about the difference between estimation, intent estimation, and motion prediction. But if I don't answer this question, please ping again, and I'll try to answer it more directly. And our next question is tying back to the question about whether or not these agents can be autonomous vehicles. Yes, so the point here is really good. So So the original question was, can these same methods apply if the agent is human or if it is autonomous? So the general answer is yes. And I mentioned that depending on how much you know about the agent will really determine what sorts of methods you might use. But if there is limited communication, or perhaps you don't know that much about the autonomous vehicle, say it's from a different car maker than the one you are designing or operating on, then you would want to still capture some of these internal states, and you'd likely have to do some of these same estimation points still. So that's a great point. All right, so if there are other questions, again, feel free to drop them, but I'm going to move on to the next slide so I can answer Sharon's question here. Okay, so when we talk about intent, one of the big questions is what's the difference between intent and motion prediction or motion? So in the psychology literature, we actually think about intent as being very separate, or as being separate from whether or not you actually achieve some task, okay? So for instance, if I am trying to execute a lane change, my intent might be to lane change even much before I'm actually executing the maneuver. So there are actually some really great studies in psychology with trying to understand intent, and they work basically with children, and they show people trying to perform some task but not achieving it. So the canonical example is I have an object and I'm trying to pull it apart. So even if my intent is to pull it apart but I don't successfully do it, people are very good at still understanding the intent, and they can actually recreate the full action even without seeing it happen. So intent is more about what is the motivating goal, and it can basically, it will be what guides your reason and guides your future motion, but it is technically decoupled. But often when we talk about estimating intent, we often think about trying to estimate intent from motion cues. So usually even before we fully execute an action, there are some cues that we can kind of pick up and try and use to infer intent. And often when people actually observe motion, really as humans, we don't think about the precise state or the precise motion, but we actually think about intent. So we won't remember exactly how a lane change is executed, but we will recall that a lane change did occur. So often when we think about these sort of abstractions, this really affects how we understand what people are doing, and it has very close ties to memory, actually. But it also really influences how we react, and again, how we predict. So intention is meant to be basically one of these internal states or these representations that will then influence the prediction downstream. So they are super related, but intention should usually guide actions. And one thing that's very interesting, in my opinion at least, is that often when you are observing some continuous motions, people usually have a pretty high level of agreement over where these boundaries are between distinct actions, which correspond to intent. So one of the examples to think about is in driving. So we are, say, watching this vehicle drive. At some point, it will go from this intent of lane keeping to lane changing. And with pretty high repeatability, people are pretty good at basically marking when these changes occur. So there's usually some pretty high agreements, even if there is some gray area, sort of when different things start, there's still some pretty high agreements here. And there are a few different schools of thoughts about how people discern or how people understand intent. And they're necessarily competing, but they usually sort of take different stances and might influence how you make this inference or estimation down the road. But the first would be that intent arises from some invariance. So this is something sort of deep and internal to motion and how we move. And the second is something that we learn this basically through experience. So basically by interacting with the world and interacting with other agents, this might influence how we make these discerns. All right, so we have some questions. Device in cars that is designed to express lane changing intent. Actually, so yes, I would say a signal is one of the good ones here. But even without using your blinker, people are still very good at estimating intent. And actually, if you remember back to our our last lecture. When the lane keeping assistance devices usually require you to use your blinker to basically not have false alarms. But whether or not people use their blinkers are sort of up in the air. Yeah. And I guess, John, I don't know about the BMW example. If you want to bring it up, feel free.
That's anecdotal data only.
Great. Yeah. Okay, so this is just a quick motivation, but so let's talk about some of the different again, model considerations that we want to think about. So again, there's really no one right way to perform this intent estimation, but there are sort of three key things that all models will try to define and will sort of help understand where different approaches can be found. So first, you have to define your intention space. So this is basically what are the different intents that you are considering and how do you represent that? The next is basically how do you represent uncertainty in your intention hypothesis? And then the final one would be how do you actually perform the inference? So now that you basically have your problem defined, how are you actually going to do this estimation for what the intent actually is of the agent? So again, so we're going to talk about what some different common approaches are, or different approaches people take, but we won't talk about specific papers. But if you do want the specific papers or approaches associated with any of the different approaches, at the end I'll share basically this survey that has links to many different papers on all of these different pieces here. All right, so the first one is intention space. So almost always intents are defined explicitly. So engineers who are designing their model or trying to come up with their approach, they will explicitly define basically a set of intents that will be considered in their model. Sometimes they are learned in an unsupervised manner. Suppose you maybe have some trajectories and you cluster them together. But that is sort of a rare case. They're almost always defined by the designer themselves. And they're often associated with things like route mode behaviors. So some of the examples we had before were things like turning right or lane changing. There are things that are basically specific to the route. And these will basically specify or set what your goals are. And there might be some other aspects that influence this, like perhaps some tendency to avoid tolls, not poles. And that will basically come into play when we think about what these route behavior modes are. Sometimes they are defined not necessarily by these route behaviors, but by configurations specifically. So basically, given the current layout of the scene, they can basically just be designed in a very spatial way here. For example, it can be dependent on the road structure. So you can define it by some roundabout or by in relation to other agents. So this is something that's a little bit more dynamic, but is set basically at different times based on the scene itself. You can also think about these in terms of action. So I think this is one of the most sort of intuitive ways to think about things. And this is something that might be related to some of the route behaviors, but often are more inherent of just some sort of underlying goal here. And all of these different intents are likely to be context dependent, and they might evolve and change over time. And then there are some things that kind of have some interesting blur. So for example, we can think of a lane change action, but there might be very different reasons for it. So it might be because you need to take a right turn in the future, so you need to execute this to achieve your destination. Or maybe you're just behind a slow car and you want to perform an overtake. So there are basically many different things that kind of can overlap or blur these different pieces together. And you can even say, incorporate some of these spatial constraints or configuration things into these other pieces. But often when you're defining them, you try and sort of pick one as your main goal and move from there. All right, so now that we have our intents specified, the question is now how are we going to basically represent the uncertainty or the facts that we are trying to estimate this and we might not have perfect knowledge about what the intent of the agent actually is. Okay, so the big question is how do we represent this uncertainty? So basically we want to know what the probability of a specific intent is. Sometimes this is just represented as the probability of this internal state. Often it's conditioned on your observations as you're sort of making this inference, which is in the next slide. But the most common is, since we are often defining a discrete set of intents that you might take, this is almost always represented as a discrete probability distribution. So again, we have some probability that is assigned to each of the different modes. But often when we're tying this to some sort of motion or trying to tie this to prediction, even this sort of discrete probability distribution is converted to a point estimate. So at the end of the day, we often assign just a probability of 1 to a single mode. Because often, because we have these sort of discrete actions, when we try and think about what this means downstream, often mixing trying to do some mixing strategies doesn't necessarily result in anything meaningful. So if I have lane keeping and lane changing, if I kind of try to do some averaging or mixtures, I might not get a meaningful prediction out. Does this
the question from the chat there from Benny is whether intents must then be designed to be mutually exclusive?
So usually they are, but they don't necessarily have to be, but usually they are.
And then a second question here from Lawrence. What does mode mean in this context?
So often when I say mode, I mean a specific intent. So sometimes different intents are associated with modes of behavior, which are sort of these sort of different sort of classes of behavior. So if I say one mode or another, it might mean lane keeping versus lane changing.
Yeah, so I think Benny maybe wanted to follow up a little bit on his question. So Benny, at your leisure, go ahead and unmute.
Yeah, thank you. Can you hear me? No? Yeah, okay.
Yeah.
I wanted to quickly just, if I wanted to do it, right? So you say it's a probability distribution over the intention set. So first of all, I need to formulate the intention set, right?
Yes.
And second, if I want a probability distribution to be summing up to 1, right? To be mutually exclusive, right? I either do that
Yes.
or I do that, right? So it's required for this to work.
Oh, yes. Yeah, that's a good point. Yes.
Okay, good. So if I have intents that are sort of synergistic to each other, I have to separate them out for this framework to work.
Yes. Yeah. And
Okay,
I think
good. Yeah.
that's since you are defining what the intentions are, and again, usually this is done by the designer. Usually that's not a huge amount. So usually because you are the one that's designing it, basically whether or not it's mutually exclusive or not is straightforward.
And that also works on an subset, right? I could say the rest is other intents. So if I only care about 10 of them, it's just the rest is just the tail, right? Of others.
Yeah. Okay. So I think that is less common though, because usually, we'll talk about sort of the different methods for for the inference paradigms next, but probably the most common, or one of the more common approaches, is to do some sort of supervised approach. So usually you do, I guess, so then you could assign a other label, but usually you do, I think it's very rare that you have a other model.
Okay, great. Thank you.
For the question about the point estimate, so depending on how you basically decide what the point estimate is, it is usually associated with this highest probability one. So usually you take your distribution or if you have some estimate and some probability associated with each one, usually you convert it to the point estimate basically by just taking the highest probability one. Yes. All right. So unless there are other questions, we'll keep going. Okay. Some other representations are with particle distributions or something that's a little bit more non-parametric. So let's keep moving. So for the inference paradigm, so again, the big question here is basically how are we actually going to start inferring what the intent is, now that we have our representation and our definition of what the intents are. One really common approach is basically a single shot estimator. So as I mentioned, this is basically something where you have often a classification method where basically at each inference step, you're going to take some time window and you want to estimate what, or try and classify or identify what the intent is at this current time. And we call this single shot estimators because you're in these approaches, you often don't try to basically build on your estimation over time. So each time you perform this, this estimation, you're not using any past observations in the past. Your input might be something like a window of time. So you might inherently be taking some previous information into account, but you're not building on the output of the estimator explicitly. Besides classification type approaches, another common method is to do things like generate prototype trajectories, and you do some matching between what you have just observed to previous ones here. So single shot estimators, again, you can kind of think of this as often a supervised method. And one of the, so it seems like when you think about what inference or what estimation is, this is often sort of counterintuitive because usually you want to try and build more confidence over time and build on what you've observed in the past. But single shot estimators are often quite good because humans change their intents all the time. So often if you're building confidence in something, if it suddenly changes, then basically the previous information is no longer useful. So even though it seems at odds with a lot of the estimation and inference ideas classically, they often work comparably in practice. But so that brings us to our next one, which is this idea of recursive estimation. And this is basically a very broad view, but this is where we are taking our last or our current estimation of what the intent is and trying to basically build on this. So we receive new information and we want to update based on this new data that's received. This is often very related to Bayesian models, which basically say you have some prior and you want to update it based on what you're observing. So single shot estimators are very, very common, especially as learning is becoming more prevalent. But I think still one of the most common approaches is to take some formulation of a Bayesian approach, perhaps build some graphical models and do your inference based on this. Another common approach, and again, something that's gaining more attention lately is black box models. So this is most learning approaches where you take these observations and you want to make the inference of what the different class is. So these are often non-interpretable, and you usually have to have some sort of data set to do this. And I would note that these aren't mutually exclusive by any means. There are many black box models that are recursive, and there are many black box models that are single shot estimators as well. The last point here, so I call it here game theoretic models, but really this is basically approaches that try to take into account all of the different agents into account to compute or refine these intention hypotheses. So this one is a little bit more, this probably isn't the best name for it here, but this is basically where we're trying to cast it more as an optimization problem and thinking a little bit more about how these agents interact. So we have a question. So what of those is the closest to what humans actually do while driving? So this is a great question here. So I think there's sort of a combination, and I think there are many competing views on what people actually do. And actually, if we go back just a few slides here, part of it comes to some of this question here. So there's how people discern intent is a big question in the psychology community. And this is a big question for cognitive science. And actually, so this paper here it's from the cognitive science community, but they do a really good job outlining, and it is a little outdated, but they do a great job looking at from the psychologist perspective how people actually determine what intent is. And as I mentioned, there are sort of two competing views. So some people view this as some invariance in structure from action. and some build more on this inferring. So if we were to take these different views and now try to classify it as a paradigm, there are basically two different sort of competing methods here about whether or not people do more just take some observation window and classify it. So if there's just some invariance that you just need to find, and that's sort of this inherent thing that's part of being human, or if it's something we learn sort of by experience, and that would more motivate some of these black box models. For some of the game theoretic things, there are some studies that show, that look at sort of how many like levels of reasoning people go into. So how many sort of considerations do they do when they're considering interactions with other agents. But I don't know how generalizable some of those insights are.
So while you were addressing that, I think another question that came in was about time complexity. Is that a factor to choose the correct model here?
Yes. Especially as you think about, if you're thinking about a single agent in isolation versus trying to make the inference over a whole scene, really influence basically what the different methods can have. And often, especially when you're thinking about things like whether to do some sort of learning-based or black box model or something that's perhaps a little bit more formal, often it depends on how, whether you have, say, more data or more reliable models of what's going on. So depending on what you have access to will also determine sort of what is feasible given these different methods. And so there are some questions in terms of sort of time complexity, but for many models, the once you have your system, the forward guess or the forward pass where you're doing the estimation is quite quick. So usually, at least computation time is not a problem. It is a problem in the generation phase, though. Yeah. Any other questions? All right, great. Okay, so the next bit is on driver traits here. So driver traits are really important, especially when you think about things in sort of simulating or trying to recreate human behavior. So here's a quick view of basically, this is just a simple loop of drivers driving in a loop. But if you didn't have many different traits or many different ways to represent different types of driving, this would be a very boring simulation. And well, I wouldn't say maybe it's that exciting now, but it's more exciting than it would be if we basically just had one general driver. So often when we think about traits, we want to start thinking about basically how do we characterize some of the more nuanced or differences inherent in drivers. Okay, so similarly for the trait estimation, we have basically the same different things that we want to consider. So we have our trait space. So we want to think about what are the set of parameters and the values that the model might pick. We want to think about how to represent the trait hypothesis. And again, think about the inference paradigm that we'll use. Okay, so we can go basically through these. This one's a little bit quicker than some of the intense things. But for the trait space, so often we think about this as basically some of the internal parameters that guide how people maneuver or how people control their vehicle. So one of the most common ways to represent this is as tunable policy parameters. So you can have some parameters that you can tune to account for things like style or preference. And we as designers often sort of connect these to some sort of intuitive behavioral traits. So we will sort of be able to set these and say, okay, we think an aggressive driver captures these certain styles or preferences. So one of the common examples is the intelligent driver model. So this is one of the most common models for simulating driver behavior. And so we have these different parameters that will govern your acceleration as a function of things like relative distance and velocity relative to a lead vehicle. So we can sort of tune these and set them to different things. So we can basically tune these parameters and what's received as either aggressive or distraction. And when well, I guess politeness is more associated with lane changing, but we can take these different parameters and tune them ourselves and sort of assign them to different traits. So again, this is something that as the designer, we are often doing. So there are some parameters that you can introduce that can try and capture or model attention. as well as perhaps some physiological traits. And I think reaction time was mentioned as one of these things as well. So again, often you can sort of figure out different ways depending on what the controller is you're assuming. You can basically tune these different parameters based on this. If you want a little bit more of a hands-off approach and you are assuming that your agents are utility maximizers, you can basically set a reward function, and you can encode things specifically like driver preference, and then you can find the policy that will maximize this reward. So the reward function is usually a fairly flexible way to sort of just quickly set where you think people's incentives or costs might be. Another common approach is you can, if you are using some sort of black box policy, you can sort of think about some of these black box approaches as an implicit representation. So even though we don't necessarily have the insights, if you do have these sort of hidden variables within, these non-interpretable parameters can be viewed as driver traits if you're really willing to let go of interpretability there. But some people sort of view it as this. Okay, so the trait space is a little bit harder to define in this case. Oh, we have a question. Go ahead, Benny.
So I'm a little bit unclear both on what are the timescales on which one is talking about, given that, for example, sometimes you drive, or at least I'm sort of doing it automatically, not thinking, right? And then sometimes I'm suddenly very strategic again and think about, oh, this, I actually want to overtake. I didn't notice this the last minute or something, right? So these can change over time. The other thing, of course, how ethical is it actually to estimate traits, sort of like classifying drivers in certain categories and saying, this driver appears to have a longer reaction time or shorter reaction time. Should I exploit this, right? Explicitly exploit this.
Yeah.
It seems like there's a lot of concerns there as well, right?
Yeah, that's a great point. And I think that's, so I don't know if it's exactly because of the ethical considerations, but I think because it's a little bit trickier to do, and there is some uncertainty about how you actually use this, I would say estimation usually takes much more prevalence over trait estimation. And I think you raise a really good point with the ethical considerations, especially when you start thinking about when cars are deployed. Usually you want to have a car that will sort of have some edge over other agents, and hopefully that isn't something that's it. But I could very easily see how it could become that. So I don't have a answer, but I think that's a really excellent point. I think that's something that's important to consider.
So if one decides to do trait estimation and then use them somehow, then the second question is, how would one in practice do that in terms of timescales? Would one just say every driver has, or driver car combination has traits, period? Or would they sort of change on a timescale of a minute or something like that?
Yeah, so that's a good question. So I think, and I think this is covered in one of the later slides, but so intent is often estimated online. So this is something that you're constantly trying to estimate. Traits, so for the hypothesis, this is almost always a point estimate. So you just basically have what you currently estimate your trait or something to be. So you usually have this thing that is assigned or sort of set online. It is, or estimated, and you just have basically one value that's associated with it. So traits themselves, they are, since they are more commonly used in things like simulation, they're usually determined beforehand. And once you sort of have your estimate, they set. And maybe you do some sort of update online, but usually they are more constant. So how frequently it should be updated, I think, depends on the focus of the model itself. But usually they are more set and something that's a little bit more inherent to the server. So even though it can evolve over time, it is less common to actually do that.
And slow time scale, like how tired somebody is or something.
Yeah.
Okay, great. Thank you.
Great. So I guess for the hypothesis, as I mentioned, these traits are almost always a point estimate where basically you just have one set of parameters that is sort of your current estimate of the different traits. Okay, so now to the question of online versus offline. So often they are computed offline. So these are something that are computed or set offline. And again, because this is often used for things like simulation, these are often something that remain fixed during some operation. You can do this online where you reason about the traits in real time based on some current observation, but usually you try to settle on some sort of traits because usually this is something that is viewed as a little bit more static. There are some methods that do combinations where you have some prior or some sort of initial set and then you do tuning online. But again, I would say that the sort of offline estimation is the most common here. When you're trying to do some of the inference, sometimes they are just tuned heuristically or set there. That doesn't really mean correlate well with inferences, but usually you have some sort of set, or often you'll have some sort of set rules that will help you determine sort of which of the following types of drivers you might be dealing with. You can also use some sort of optimization techniques. So often you can use something like regression to just do some estimation or match some offline data. And similar to trying to tune different things like finding or saying what the reward function is, you can use inverse reinforcement learning or inverse optimal control to try and observe different driver behaviors and try to infer basically what the different drivers mean. Or what their different traits or underlying sort of values are here. And again, they can adapt and change and they might be contextually varying, but as was brought up with Benny, this is something that is very difficult and hard to do in practice. All right, so in this last few minutes here, if I can take maybe 10 more minutes or so, let's go to motion prediction. But again, if anyone has questions about traits or anything else, feel free to drop notes in chat. Okay, so for motion prediction, again, this is often what we think about or what one of the most important parts are. So once you have some sort of understanding of what is influencing the policy and what the intents or goals of the agent are, often the goal of all of this is to eventually get a good prediction of what the agent might do. Okay, so different considerations might be, what are the vehicle dynamics models? So basically what is going to be propagating these states forward in time? Again, how is the uncertainty modeled? So some people view scene level predictions. So instead of just thinking about individual agents, they'll propagate the whole scene forward. We won't be talking about this. We'll just be talking about basically the agent level modeling. And again, we have the different prediction paradigms that we might be using. All right, so very quickly, so the vehicle dynamic model, so often this will sort of set what your future prediction looks like. And I think one of the more common things that we think about is propagating vehicle dynamics forward. So there are many, very good models of vehicles. So if you know the vehicle itself, you'll be able to basically estimate things and you can make sure that things are dynamically feasible. However, in practice, because you're often observing many different vehicles and many different agents and you don't know many of the parameters, you often don't see this used that frequently. So often you don't necessarily consider the specific physics of the agents, although you can if you have some insight or if you are operating in relatively controlled conditions. For example, if you are doing lane keeping on a highway, often you don't need really high, you don't need many other parameters to understand the physics of the agent. You can represent these trajectories as splines. So you basically have some parametric curves that you try and fit to specific points. So you can basically get a more fluid trajectory. So it might not match what the vehicle can physically do, but it does capture smooth trajectories that people often actually carry out. So these models are often assuming that you have some sort of continuous model or some sort of finer trajectory that you're trying to predict. But you can also do a similar thing in discrete state transitions. So maybe you're working on a higher level of abstraction And that gets a little bit closer to trying to infer intent, but you can similarly think of these different predictions sort of on these more discrete levels. And this ties very closely to things like Markov models. So very similar to the framework that we presented before, you can think of basically trying to fit this model more precisely and thinking about how that propagates forward. And again, you can always represent the model as some sort of black box where you have some learned model that is perhaps less interpretable, but might be able to capture some things you observe. And depending on the different types of model and what the goals are, this might guide what your underlying principle is. All right, but this really depends on what your agent level representation is. So when you think about prediction, there are often different ways you might want to represent the prediction, and this will highly depend on what you actually want to do with it, downstream task, or what that sort of goal is here. So probably the most intuitive prediction you might want is a single trajectory. So we have our agent, perhaps we understand that we've inferred that it wants to change lanes, and we want to predict the motion that's associated with it. So this is something that is sort of like our ideal, this is what we want to do, but it's often very difficult or challenging in practice to get the exact trajectory out. But this is often sort of the precision thing that people most commonly try to shoot for. And again, this trajectory can be something that is dynamically feasible. So this can be based on some model of the car, or this can be something that is just a parametric representation, something like a spline. Often if you're thinking about this from the perspective of perception, you will take this and you will convert it to something like bounding boxes. So you'll basically try and propagate these bounding boxes or detections of an agent forward. This is often nice because you can tie it to nice techniques for motion planning and trying to map these things to things like occupancy grids or something that you might use for planning. Okay, so if you, another representation is distributions over trajectory. So instead of just trying to guess the precise trajectory that the agent will follow, you want to try and capture some of that uncertainty. So this is often very useful because this will help you capture some of the risk or perhaps some of the notions that you might not be capturing everything perfectly. So you can either have this as a unimodal prediction based on the intent or just a single trajectory moving forward, but you can also do a mixture. So if you do maintain some distribution over different types of intents, you can have different modes of behavior. So in this case, this car is trying to be predicted, and you can see there's two potential trajectories that they might take and some uncertainty associated with it. So you can have these mixture models as well, but it's often tricky to determine what you actually want to do with it. But again, if you want to capture some sort of risk or try to capture some of this uncertainty, this is some of the best ways to do it. Similarly, you can represent any of these distributions with a sort of sampling-based approach, where now you have something like particle sets. Perhaps you have some model and you want to sort of propagate these forward. You can basically forward predict a bunch of samples through your agent and represent these as particles or sort of potential outcomes of your system. The last potential method that I have here is a set-based representation. And so there are often two approaches that are used. So the first is an occupancy grid-based approach, where again, now you're trying to think of trying to connect this to mapping representations that are commonly used in motion planning. So in occupancy grids, you try and basically think about which states are occupied or may be occupied in the future. So you can basically dilate your prediction to cover these grid cells. So this also often gives you a set of states that you might, that the agent might be in. And that's visualized here. Or you can use some reachability-based techniques where you now propagate things through the dynamic model itself to try and basically come up what the likely sets of states might be. And again, you often try and bound for something like worst case. So this is often associated with something like risk aversion. Okay, so for my last little bit about motion prediction. So often when we're doing this prediction, we want to say for some time horizon, so you usually have a fixed time horizon that you are looking over. You usually assume that at least for this time horizon, your intents and traits are fixed throughout this whole whole window here. So if you're thinking about sort of the rate at which these different intents and traits are updated, they're usually sort of associated with your time horizon on the prediction itself. So one of the most straightforward or perhaps naive ways to perform prediction is to do an independent prediction. So this means for each agent you are estimating, you take your observations and you basically just do this prediction independent of other agents. And so you basically do this sort of in a one-off piece. So you can kind of think of this as being open loop. And the predictions themselves often degrade quickly over time. But in terms of things like computational complexity and how to actually generate the models, this is still one of the more common approaches here. If you do have a closed loop trajectory, you can do forward simulation. So if you have these closed loop control policies for each agent, or you have some idea of how they react to different inputs around them, you can basically simulate and forward to roll these different trajectories out for each agent. I will say that just because you have a closed loop policy does not necessarily mean that you won't have prediction degrading quickly over time. So here's a quick example. Let's see if it'll restart of even if you have a closed loop simulation for the different agents, depending on how good your prediction is and how just your prediction itself degrades over time, you can quickly get these sort of very clustered or things where they just sort of start going wrong if you look over long time horizons. So often this is something that you want to consider when you're tuning your time horizon here. So we have a quick question here. So would this mean that the intent must not be weave around obstacle, but it must be weave around obstacle on its left side? Yeah, so this is a good question. So often when you think about things like overtaking or lane changing, you usually separate out the directions that you move. And this is actually one of the big problems, because if you don't specify it out and you have some uncertainty, sometimes you have some weird things where you kind of end up doing nothing in between. So yeah, so this is a good point. So usually you do assume one way or another. All right. So the last method that I would say is the sort of final approach here is, so again, if we loosely use the term game theoretic, but have some sort of interaction aware policy, this is like an extension, I would say, of the closed loop policy, where you're not just constantly taking the current state and doing some update, but you're really conditioning your future motion on the reactions and future motion of other agents. So you have more of this level of recursive reasoning, and you're trying to sort of understand these influences here. So in the sort of traditional game theoretic case, you have your models for the different agents. You want to compute over all of these different possibilities and find some equilibrium. In practice, that's really not feasible for driving, but you can do some approximations. But I would say probably the closest, one of the more common sort of in-between approaches is something like model predictive control, where you do have some prediction of all the different agents in your environment for some fixed time horizon, but you're constantly computing everything. So it kind of recreates some of this closed loop and interaction policies without having sort of the heavyweights of everything else. All right, so that's the overview of the different driver modeling tasks that we have. And so just to give a quick overview of what we've talked about, we talked about this framework that basically allows us to catalog these different methods or sort of categorize and classify these different approaches or pieces of modeling into a formal framework. So we can kind of think about the relationships between everything in sort of a concise way. And since I am fairly low on time, I don't think we'll talk too much about pedestrian prediction, but so I'll just in maybe a minute quickly go through it. So the ultimate paradigm is actually very similar. So you have many different inputs that you can use. Again, the prediction method itself is very variable and can actually tie back to what we talked about before. And similarly, you have these sort of different predictions that come out. So basically all of the representations we had before still carry over. Often one of the biggest distinctions that we consider is basically the perspective that you might take. So you can either look at a top-down view which isn't as meaningful for something like autonomous driving, but often in the general sense, this is sort of a nice viewpoint to think of it. So we can basically think of these as points moving. And more relevant to the driving case, we think of a first person view. And maybe as just a sort of a quick last slide here, I think one of these sort of interesting things about pedestrian prediction is even though they're much harder to use or apply physics-based methods to, so it's much harder to basically identify what the dynamics and control inputs of a human are. So things like the social force model try and capture some of these different pieces. And it's still one of the best methods for modeling pedestrian behavior. So even though we have lots of data and there's lots of learning methods, the physics-based or things like the social force model are still getting sort of higher accuracy for a lot of these different pieces in some of the sort of test beds and comparisons. But so I'll stop here actually. So we'll go to my final slide here. I have some other references and notes sort of in some extra slides, and I'll share the slides so you guys can go through some of these other things as you want. But with that, I'll open it up for questions. If anyone has anything else they'd like to ask or chat about.